Hello students, welcome to EPG Pathsala. I am Professor D. Velmurugan, former head of the department from Center of Advanced Study in Crystallography and Biophysics, University of Madras, Gindy Campus, Chennai, and I am at present working there as the University Grants Commission Basic Scientific Research Faculty. Today we are going to talk on module dealing with the tutorial on hand propagation, particularly for the centrosymmetric case, and this comes under the paper biocrystallography. So students, let us see what we are going to learn in this module. First, I am going to introduce you to centrosymmetric and non-centrosymmetric cases. Then I am going to teach you what is meant by Sayer's equation and how he used the sign relationship derived by him to get the signs of new refractions, and also how to do this finding of signs for the bulk of Bragg refractions without the knowledge of the computer, using hands only, which is known as hand propagation of sign relationship. So let us consider now the centrosymmetric case. David Sayer in 1952 proposed an equation for obtaining the algebraic sign of a reflection H, that is either plus or minus, knowing the signs of the other two refractions K and L, such that these three reflections H, K and L have a relation H plus K plus L is nearly equal to 0. Actually, the exact relation only. When I say H, K, L, you should not confuse. When I say capital H as a reflection, I mean a three set of Miller indices, little h1, little k1, little l1, and by capital K, I mean another reflection with indices little h2, little k2, little l2. By capital L, I mean the third reflection with indices little h3, little k3, little l3. All these little h's, k's and l's can take any value, but only integers, positive or negative, including 0. So being the case, automatically when you add these three reflections H, K and L, that is what is meant by H plus K plus L, we can definitely get certain combinations of these three reflections such that H plus K plus L is exactly 0. What do you mean by H plus K plus L equal to 0? Little h1 plus h2 plus h3 should be 0. Little k1 plus little k2 plus little k3 should be 0. And also little l1 plus little l2 plus little l3 equal to 0. So these three are the sub-conditions of the main relation H plus K plus L equal to 0. Only under this condition we can apply the Sayer's equation to find the unknown sign of the third reflection from a knowledge of the algebraic sign of the two refractions. Here, all the atoms are assumed to be identical, and the hypothetical structure is called the squared structure, where all the electron densities are squared. If the atoms are considered sufficiently far apart, then their electron densities do not overlap. So they will be like this way, do not overlap to an appreciable extent, and the squared structure also consists of equal spherically symmetrical atoms whose scattering factors may be calculated exactly as a function of H or sin theta by lambda. Peak positions will be the same in the squared structure as that of the other structure. The Sayer's equation is f of H equals 1 over capital V times little f over gamma times, in the numerators, summation over k, fk, fh minus k. So here each is a structure factor. One corresponds to structure factor f of H reflection, another the right hand side corresponds to k reflection, another corresponds to the structure factor corresponding to H minus k reflection. If we just see these H or k or H minus k, each one of these three reflections denote 3 Miller indices each. So by capital H I mean a reflection small h1, k1, l1. By capital K, I mean another reflection, small h2, small k2, small l2. By capital H minus k, I mean a third reflection, which is h1 minus little h1 minus h2, comma, little k1 minus k2, comma, little l1 minus l2. So you should not have any confusion in this. Now, in the above equation 11.1, the little f corresponds to the atomic scattering factors of atoms leading to the electron density rho of r, and this nu is that corresponding to the electron density rho square of r, and capital V is the volume of the unit cell. If you assume that you have electron density, a set of numbers will be there. Then these are contributed by this atomic scattering factor Fj. Now you assume another density where these numbers are squared, that is called rho square of r. So definitely this density will not be coming from f of j, but because of some other term gamma. So that is called the difference. Such a factor corresponding to electron density depends on little f, and corresponding to squared of electron density, it is a function of gamma. Now, starting from this equation, we can derive a simple equation called sine of h reflection times sine of k reflection times sine of h plus k is nearly positive. It is nothing but a multiplication of the sines of three reflections. Why you call it the probably positive? So these are all coming under the field direct methods. Direct methods have so many assumptions, and because of which nothing is exact. So that is why we talk probably. So when we talk about this picking up the sign relations, we pick up usually those relations having a validity or having a probability above 95%. Then only they are supposed to be valid. When I say S of H, it means algebraic sign of reflection H. So here we consider mostly centrosymmetric cases where the reflection will have a sign plus or minus corresponding to the phase 0 or pi. As we have seen from the beginning, the ultimate problem in crystallography, the bottleneck in crystallography is that the Bragg diffraction gets the intensities from which you have to take the square root and get the amplitude of Bragg reflection. But your ultimate aim is to locate the atomic positions, for which you have to compute the electron density at various points, and only at the atomic sites called Rj or Xj, Yj, Zj corresponding to the jth atom, the electron density will be maximum. But unfortunately, to do this calculation, one has to know not only the such effect amplitudes of Bragg reflections coming from experimental measurement, but also the individual phases of these Bragg reflections, which is not coming from experiment. This is one of the bottleneck called phase problem in crystallography, and direct methods based on certain assumptions, they derive some phase relationships or some sign relationships from which they initially determine the structures which are centrosymmetric, and later the structures which were non-centrosymmetric. So that is the thing we are covering as a tutorial now. Larger the such effect amplitudes of these reflections considered in 11.2, larger will be the probability for the product of the three signs to be positive. Using the above equation and knowing the signs of the reflection H and K, the sign of H plus K can be found. So let us consider an example. As all of us know, centrosymmetric case, the phases can assume only two values, either 0 or pi, whereas in non-centrosymmetric case, the phases can go anywhere between 0 to 2 pi. So the such a factor f of h, which is generally defined as amplitude of f of h e power I phi of h, will have simply plus mod f h or minus mod f h, because when this phi of h is the exponent becomes 0, e power I of phi of h becomes e power 0, which is 1. So sign is plus for amplitude of h. When phi of h is pi, we have e power I pi, which is equal to cos pi plus I sin pi. Sin pi is 0, cos pi is minus 1. Therefore, f of h becomes minus of mod f h. That is why I am telling, in centrosymmetric case, depending upon the two phase values or phase choice is 0 or pi, the algebraic sign of the such effect amplitude becomes plus or minus. So that is why you say centrosymmetric case, phase problem becomes the problem of assigning algebraic signs to the such effect amplitudes obtainable from experiment. Reflection H and K are chosen from the origin defining reflections for which already you have assigned the phases or signs. For strong reflections, Sayre equation can also be written as sine of h times sine of k is nearly equal to sine of h plus k. So if you know the sine of h reflection and sine of k reflection, you just multiply these two signs to get the sine of h plus k reflection. So this is called hand propagation, because in earlier times, 40s, 50s, 60s, when there was no computer, people used to do this phase calculation by hand. This is known as hand propagation. Why is it called propagation? Assuming the phases or signs of certain centrosymmetric reflections are known, then they slowly extended the procedure using Sayre equation and other formula to get the sign or phases of the remaining bulk of reflection, that known as sign propagation. So let us consider, suppose sine of h is negative, sine of k is positive. As I already told, when I say h, k or h plus k, each means a reflection which is a three-dimensional value, hkl, small k, small l, where these values can take 0 or positive or negative integer. Now if we consider the first reflection h sign to be negative and the second reflection k sign to be positive, then the product of signs will be positive. If you consider sine of h as negative and sine of k as positive, then sine of hk will be negative. Suppose you consider sine of h as negative, sine of k as negative, then sine of h plus k will be negative times negative positive. So simply the third reflection h plus k sign can be determined in terms of the two parent reflection h and k if the signs are known. Let us consider the non-centrosymmetric case. Although the equation 11.1 is not strictly valid for unequal atoms, but in unequal atoms, the species will not be the same, maybe carbon, nitrogen, oxygen, which differ in the number of electrons. The criteria that the atoms in a structure are identical, symmetrical, and do not overlap in space will lead to diffracted amplitudes and phases that are connected by exact equations. One can now obtain from equation 11.1 the probability relation. That is why we are in 11.3 we are getting the relation approximately equal to 0. Probably. The probability relation is phi of h plus phi of k plus phi of minus h minus k should be equal to 0. So you should not confuse with the term minus h minus k, because previously we know that h plus k plus l equal to 0, from which we get h plus k as minus l or l as minus h minus k. So that is the assumption you have to make. Now, when the normalized structure factor amplitudes mod EH and mod EK are larger, then phi of minus h minus k is probably equal to phi of h plus k. Now, equation 11.3 can also be written by taking the last term in equation 11.3 to the right hand side. That is how you can write a relation for the phases for the Sayre equation as phi of h plus phi of k is nearly equal to or probably equal to phi of h plus k. What does this tell you? By knowing the phases of two reflections h and k, I can get the phases of new reflection h plus k. The above equation is used in phasing non-centrosymmetric structures. Phi of h and phi of k, the phases of the two reflections capital H and capital K, are known as they are usually selected from the origin defining reflections, and knowing these two phases initially, the phase of the new reflection L or H plus K can be calculated. Let us consider some example. If phi of H is pi and phi of K is 0, then eventually phi of H plus K equals phi of H plus phi of K, which is equal to pi plus 0, which is equal to pi. And if phi of H is pi and phi of K is pi, then again phi of H plus K equals phi of H plus phi of K, which is equal to pi plus pi equals 2 pi, which is equal to 0. So now I am giving you like a homework now to appreciate the hardships faced by the senior crystallographers who are no more. You have to do whatever calculations they have done in the 50s. They took years together to solve some structures. To appreciate their hard work, to honor them, I given some data. This is usually provided by the wife of the Nobel laureate Professor Jerome Karl. she is Professor Isabella Carl. So whenever she gives a tutorial, so she used to give this. I'm just circulating this. So here I want to honor Professor Isabella Carl in the context that even though the direct methods developed by Professors Carl and Hoffman in the 50s were popular, nobody was ready to accept it because the basic assumptions were against the principles of physics, namely the non-vibrating atoms, non-vibrating point atoms, and like that. Equal atom case, everything. All atoms are made of points, they have same scattering pattern, non-vibrating, and so on. Because of these assumptions, the physicists didn't accept, even though they gave an answer to the phase problem. But it is only Isabella Carl who in 1966 used the mathematics developed by her husband, Professor Jerome Carl, and also by Professor Herbert Hoffman to come out with the actual solution of a structure, a dipeptide, and she proved that direct methods could work. Thereafter only, the people who have been vehemently opposing, that is from University of York, England, they started the computer program, and first automation came only in the year 1972. So we have to honor those people, no? So that's why I'm giving a tutorial. Before that, I'm giving you a clue how you have to proceed with the tutorial. So now if you look at a table 11.1 shown is here. So what it means is, whenever you solve a structure, we have the structure factor amplitude available, and there is a graph known as Wilson plot about which you have already seen. So using the scale factor and thermal factor, we can convert the structure factor amplitude corresponding to the real atom picture, spherical atom picture, to the nominal structure factor amplitude corresponding to point atom model, which is used by direct methods. So every reflection has an E value, nominal structure factor amplitude. So that you take the average for all reflections, then amplitude of the E square minus 1. Then you take average for all reflection, then average E square, take the case for all the reflection. So experimentally, what do you get for a given structure? That is listed in the first column, second column under experiment. Theoretically, using the Wilson statistics, what are the values for these quantities? That is given for centrosymmetric and non-centrosymmetric. Now we have to compare the values under the experimental column to centrosymmetric and non-centrosymmetric cases, and wherever you have the maximum coincidence, that is minimum differences, and that is the practical situation. If you look at mod E square minus 1 average, experiment gives you 1.083. For centrosymmetric, theoretical estimate for that is 0.968. Non-centrosymmetric is 0.736. Your experimental value is closer to centrosymmetric, theoretically predictability, which means that your structure is centrosymmetric. So this is known as test for centrosymmetry. So by mistake, if you consider instead of P1 bar P1, instead of centrosymmetric, non-centrosymmetric, now change it to centrosymmetric. So this is a clue. You have to do that. Now, again, as I have been repeatedly telling, in case of centrosymmetric case, the phase problem is very simple. The phase can take only 0 or pi, or the algebraic sign of the structure factor amplitude obtained from experiment has a sign, algebraic sign plus or minus corresponding to 0 or pi phase. Here, whatever we listed, this is known as starting point for a structure determination or phase calculation using direct methods. If you look at this table, I have indicated by H vector the three serials where the integer can be positive or negative, or inverse reflections are also there. Then the phase values are given because centrosymmetric, the top three reflections I assigned a phase of plus for all the three. And usually the direct method, based on the probability thing, whatever prediction you make using direct methods, we want that to be highly probable, which will happen only if the nominal structure factors of these H vectors considered are very large. So usually we take E values greater than 1.5 or 2. So we look at these three E values, these are very large. And these are chosen as origin defining reflections, which means that I assume as if I know the three phases of these three reflections. Now, for the remaining 5 refractions listed, I have used symbols A, B, C, D, E. Since it is centrosymmetric, the symbols can be either plus or minus. Ultimately, you have to estimate the values of symbols of this A, B, C, D, E finally. So look at these E values. These E values are also strong about 1.5 because this is again and again repeating direct methods work on probability theory, and the probabilistic validity will be maximum when the E values are larger. So what I am going to prove now is, once you have determined the values of A, B, C, D, E, I mean algebraic signs, the rest of the reflection, maybe 50 or 60 reflections having strong E values, they are all indicated in terms of the signs of these 5 symbols A, B, C, D, E. That is why it is called a symbolic addition procedure. Assuming you are having a small symbol of 5 symbols for 5 reflections, we are getting the symbols, I mean the signs of remaining bulk of reflection from this starting set of reflections. In addition to choosing 3 reflections and fixing their signs, either plus or minus, 5 more reflections are chosen for origin fixing, and their algebraic signs are initially assigned as symbols, because we know the symbol can be plus or minus. So in general we assign them the symbols A, B, C, D, E and so on, where the individual symbols can have signs plus or minus, which will be estimated during the process of sign propagation or hand propagation. As I told you before we begin this, the use of computers was not possible those days, and they did everything by hand. So these types of calculations were done manually by hand, and hence these procedures are called hand propagation methods or symbolic addition procedures. Symbolic addition procedure is the same as hand propagation method, as the reflections are added using symbols for their faces. That is why we call that symbolic addition. Symbols are added. A is a symbol, B is a symbol. So these symbols can be added that way. That's a way. Now, usually all the reflections chosen for phase propagation will have their normalized success factors greater than 2.0, leading to high probabilistic estimate of phase relationship. So here we have a table explaining what are the equivalent positions. This is a P1 bar structure. So we have one molecule at position X, Y, Z, another molecule at X bar, Y bar, Z bar. In centrosymmetric case, again, as I told you, the sign of H reflection is plus, then the phase of that reflection phi of H is 0. If the sign of that H reflection is minus, then phase of that reflection H is pi. Okay. So in centrosymmetric case, we have 2 choices of phases, 0 or pi. In other words, sign of f of such a factor fh can be defined as plus or minus amplitude of fh. Amplitude is available from experiment. So we have to assign the sign either plus or minus. Clear. And one more thing is, when this H reflection is changed to minus or inverse reflection H bar, no, the phases, even though it becomes minus, since they have 0 or pi, it is immaterial, because when pi becomes minus pi, it is same as pi, because minus pi you can add with 2 pi and gives you pi. So don't have any confusion in centrosymmetric case. When you have one reflection given and phase is something, then if the whole serials are inverted, and H bar, K bar, L bar from HKL, the phase will be same in centrosymmetric case. Now let us consider slowly 2 applications. Let us consider some steps in sign propagation. Consider block 1 I am showing in the right hand side. We have a reflection 2, 1, 4. So this is considered as a capital H reflection. And another reflection 0, 2 bar, 1 bar as K reflection. If we just add H plus K, what do you mean H plus K? H if consider little h1, little k1, little l1. K is little h2, little k2, little l2. Then H plus K is simply h1, little h1 plus little h2, comma little k1 plus little k2, comma little l1 plus little l2. This is just by algebraic addition. So don't confuse, 10 bar means minus 10. So that is why 4 plus minus 10 is, we get 6 bar or minus 6. So that's it. So this is H plus K. Now the question is, if you know the sign of H, capital H, and sign of capital K, can you get sign of H plus K? Yes, that is given by Sayer's equation. So now, if the sign of 2, 1, 4, already we are given from the table, is plus, already 0, 2, 10 is given, therefore 0, 2 bar, 10 bar is again given as A. So H plus K will be simply plus times A, simply A. So this is how you just get the sign of the new reflection. Thus, your H reflection is having a sign plus, K reflection is having a sign a little a, which can be positive or negative, because of which when you add these two reflections, the H plus K reflection, which is nothing but the reflection 2 1 bar 6 bar, its sign will be plus times A, which is equal to A. Okay, this is how you fill up the sign of the third reflection. Usually the H and K are called the parent reflection. The new reflections after adding you call it as a daughter reflection. Sometimes the daughter reflection can also be used as a parent reflection if the value is known. Now we consider another block. 214 is there, already we know value. Then if you have 1 bar 1 7, but the list you have 1 bar 7 bar origin, and that is plus. Therefore, if you take inverse of this, again 1 bar 1 7, that will also be plus. Okay, so in this case 214 has a sign plus, 1 bar 1 7 also has a plus sign, though the new reflection when you add these two will have a sign of the product of the above two, that is plus times plus plus. Now consider two blocks 6 and 8. So what do you see here now? 6 block we have two sayes equals you have to apply twice, no? In each case the data reflection is same. 338 bar has been obtained from 35202 bar 10 bar as parents, and also 21 bar 6 bar and 142 bar as parent reflections. So what do you mean by this? Whenever you have such a relation and when you proceed with the hand propagation, the sign you get for this 338 bar, for example in bunch 6, has to be same. One sign you cannot get plus and another box you cannot get minus. So that is why I am giving an example. So like that we can have situation like block 8 where we have the daughter reflection 113 coming in terms of 3 types of parent serials. So all the 3 has to be having the same sign. So here also I am just giving an example how 3 daughters are there, and in blocks 16 2 daughters are there. So now let us see. You have a reflection. One reflection has A sign, other as C. Then the H plus K reflection, just don't confuse, just multiply the sign. By A we mean plus or minus. By C we mean plus or minus. When these reflections are added, the new sign will be A times C. Just put AC, don't have any confusion. So H plus K reflection will be having AC. So you just proceed in this way. Finally we can get the value of this A, B, C, D and so on. For example, suppose one reflection, H reflection has a sign B and K reflection has a sign BC. Now the H plus K reflection will be having a sign B times BC. So which is equal to B square C. So now you know this B can have a value plus or minus. Therefore B square will be having plus only. Therefore B square C will be having a value C only. Clear? So now whether it is B is having plus or minus, B square is positive. In virtue of this, your B times BC becomes simply C. So let us have another example. If your parent reflection H has a sign AC and another parent has a sign ACD, then the new daughter, which is H plus K reflection, will be having a sign AC times ACD. So now we have A square, C square, D. A whether it is plus or minus, B, C whether it is plus or minus, A square will be positive, C square will be positive, the answer is simply D. Suppose we have one parent reflection H as AC sign and K as BD sign. For H plus K, simply put AC times BD, which is simply ABCD, that's it. So don't have any confusion. You just proceed, like a homework, you proceed this way. So we can do 64 blocks are given in the output, you can do so many things. So now if you look at, the important thing is block 50, we have the same daughter reflection 3, 2, 5 occurring in 3 cases from different sets of parents. The answer you find for these 3 will be BC, BC, CD. But the reflection is same 3, 2, 5, which means that the sign of 3, 2, 5 in all the 3 cases has to be same. In other words, it means BC equals CD, which means BC equals CD, CC cancels, B equals D. This is a very, very important conclusion you have arrived at during sign propagation. Now you have reached the answer, namely, even though the sign of B can be positive or negative, the sign of algebraic set of D can be having positive or negative because it is centrosymmetric case. If B you are fixing at plus, D has to be plus. If B you are taking at minus, D has to be minus. So this is the way you have to find some clues. So now if you do this propagation, you get some relations B equal to D, then A equal to BD. So what do you mean BD? B can be positive or negative, D can be positive or negative, but by having the relation B equal to D, we have a conclusion that B and D should be of same sign. If that is the case, BD will always be positive because negative and negative multiplication positive, positive and positive is positive. Therefore, conclusion is A is positive. So now we have cleverly concluded that A is positive, sign of B should be equal to sign of D. We don't have any idea for sign of C, doesn't matter. You put C as plus in one case and C as minus in another case. Now we have the final answer for the symbols for the A, B, C, D. C, I am just putting plus plus for two answers, then later minus minus for two answers. In the first two rows, A is always plus, we know. Second two rows also, A is always plus. If you just consider the first two rows, B can be plus or minus. Accordingly, D can be plus or minus. Then if you look at the C value, that will be different. So totally we have 4 combinations for the ABCD. So now in terms of ABCD only, we have categorized the symbols for all the reflection in the which I am just going to show you. So in terms of that, we can get the symbols for the rest of the reflection which can be used in the Fourier synthesis. So that is called the Hahn propagation. Already we have given you a clue how to do about it. So you should have frightened yourself and just proceed in this way. Again, you go through the PPTs again. So now, if it is a non-centrosymmetric case, again it's a simple. Here we get the addition of phases. Phase of H reflection plus phase of K reflection will probably equals phase of H plus K reflection. But here we make use of the relation phase of H bar reflection is minus phase of H. Then other procedures are same. Let us now consider the Hahn propagation of sign relationships. We consider the case non-centrosymmetric case NC and the space group is P1. P1 space group is the simplest example for a non-centrosymmetric space group. Here, the origin defining reflections are chosen and the values are assigned as 0 or pi because it is the two-dimensional reflection, centrosymmetric reflections. Some more reflections are assigned symbols as their phases, which may be 0 or pi. The phase 0 corresponds to symbol plus and a phase pi corresponds to symbol minus. Here also, blocks of reflections H, K, H plus K will be provided. So we can refer to the enclosed table given to you in the material and use the relation phi of H plus phi of K is equal to phi of H plus K. The probably equal to sign just tells you that we have to choose only strong reflections to have a maximum probability. This relation is used for phasing of the daughter reflection called H plus K reflection, knowing the parent reflection H and K. While phasing, you have to remember that phi of H bar equals minus of phi of H. Only when phi of H is 0 or pi, phi of H bar equals phi of H. So tables are provided here, 11.1, already we have shown you. Origin deflection tables are given here. Then we have tables for the P1 bar space group. The bookwork tables are given. So finally, for every daughter reflection, you have to get the values, and knowing the ABCD symbols, you have to give all the values of reflection in terms of symbols. So students, let us summarize what we have learned in this module so far. The module introduces you to Sayer's equation and also the sign relationship. The tutorial presented in the module introduces how to do phasing in centrosymmetric and non-centrosymmetric space group manually using hand propagation method, for which I have given a data sheet. You just fill it up and master in the hand propagation procedures. Thank you.